Well, hello everyone, I'm Hugo Tyson. I worked at Acorn from 1980 to 1990, more or less, and did a variety of stuff. I'll start sharing my screen now. That's the one we want, I believe. And share. And so you should be able to see my first slide now, yay. I'll be talking about my time at Acorn, essentially. When I joined in 1980, it was at Market Hill, and towards the end, the interesting stuff I did was in the Silver Building, really, and towards the end, I was at Newmarket Road, in fact. I'll talk about the various things I did, some of the interesting questions we answered, mostly the interesting bugs that we had to fix, because that's where it was the good stuff. Finding a subtle bug is what motivates the software engineer in me, anyway. For the avoidance of doubt, all these images I just Googled and nicked off the web. So don't go selling this presentation for money later. I guess maybe. I don't know what the legal implications are. Anyway. So yeah, I started off with the holiday jobs at 4A Market Hill in the age of the Atom. I wrote Atom Invaders and Atom Snapper and worked a little bit on the Atom colour board. I'll be talking about some of the problems with that later. And then when I'd finished uni, I got a proper job at Cherry Hinton, first in the water softening plant building and then in the Silver Building, where there were BBC machines everywhere. And as I'm sure most of you know, I wrote ADFS for the Beeb by and large. Also did a lot of work on DFS, and there was some interesting stuff there that I'll be talking about in some detail. Also did some work on debugging some interesting things, which were, well, basically I was involved because it was a nasty enough bug that it was all hands to the pump, really. Then the Electron happened, and then we made the ARM, and that was about it, apart from, well, people keep using code well after you've left a company, don't they? And stuff happened involving that. So, look at that, eh? What an earnest, serious student. I was studying Maths Part 1A at King's in Cambridge, just in the centre of town there, and I'd already had an interest in computers and programming. I had a CSE in computer science because the secondary school I went to didn't do an O-level computer science. And so there I was. That's a little bit before university, but anyway, we had teletypes connected to computers in buildings far, far away. So the summer of 1980, it was the end of term, exams had finished, so I was thinking about what I should do next. So I had a look through some computer magazines, because that was obviously a lot of fun, and we, you know, some people bought magazines avidly and the rest of us nicked them and read them avidly. So there was Sinclair selling the MK14. They were in Cambridge, that was well known. So I just walked literally across the road from college where I lived and knocked on the door. Luckily, they had no jobs going, or I might have been stuck with Sinclair making a career out of, well, we all have various opinions about Sinclair's stuff. So after that, I went and looked in the magazines again and learned that Acorn existed. And that's the Sinclair MK14, as I'm sure we all know. That's the Acorn System 1, which was kind of the same thing. What they've got in common is basically a hexadecimal keypad and some controls for entering things, and a processor and a little 7-segment multiple digit display there and there on the MK14, like you would have in a calculator. And Acorn had this exciting new thing, the Atom. Fabulous. It's got a proper case and a keyboard and everything. So I introduced myself to whoever was around and said, have you got any jobs going? And I said what I was doing vaguely, and Herman agreed to talk to me briefly, and he said, what do you know about the Atom? And I said, not a lot, but if you give me an afternoon to read the book, perhaps I'm sure I'll pick it up. And he gave me a job on that basis. And in fact, this was In the morning, it was about 11:30 that I went sort of well, maybe 11, I went door knocking. And so 11:30, Herman said, well, you can have a job, and, you know, when do you want me to start? I said. He said, well, how about now? And I said, okay, but, you know, can I just pop back to college and have lunch, and I'll see you at 1 o'clock, say. And that was that. And I had a job. And I think it was something like 50 quid a week, which was sufficient money for a holiday job in those days. So in theory, I was answering tech support calls on the phone and working a little 4-line telephone exchange, by the by. As I say there, in practice, it was placating angry people who'd ordered an Atom kit with whatever the terms and conditions were for delivering the things. And there were so many orders that very few of them were fulfilled. People were putting together boxes of stuff and sending them off as fast as they can. But of course, Acorn cashed all their checks immediately. And this is what kept the company afloat and allowed it to order the parts and so on to be able to make the next tranche of kits, if you see what I mean. So yeah, Acorn was well in credit, but there was a lot of people who were very angry about the delays to their thing being delivered. The saddest case was issuing a refund to someone who had ordered one on their deathbed and had basically died before it turned up, and we issued a refund to them by posting a check off without any question. There were also comedy moments. There were people who turned up at 4A Market Hill thinking it would be a shop, expecting there'd be people in suits to talk to them, but there was just me. And you know, I said, but this isn't a shop. This is just an office. Where do we do the admin? There aren't any Atom kits here. I cannot hand you one. Please go away. And later they phoned up, or maybe they wrote a letter complaining about how they'd been fobbed off by a scruffy youth in jeans. So of course I said how terrible this was and promised to discipline the person in question, which was me all along, of course. So I'm sure, again, many of you will have seen this picture, but that was the exciting thing. Herman and Chris, publicity photo for the Atom on the lawn at King's, making it look very academic, and Herman looking very dashing and Chris looking very businesslike. But look at the flared trousers on them, eh? Ridiculous. 4A Market Hill, this building here, it's down a passageway. It's a peculiar building. For a start, it's got these weird pointy windows, but I think it used to be just like a standalone house surrounded by garden in the middle of the block, as it were. That's it there in the aerial. Marketplace is there. There's a little passageway there, and as you can see, everything around it has been built with single story, I should say, extensions, so that the only access was this passageway to a door, and then you're in it. So yeah, I mentioned fruit machines. There was fruit machines there because another one of Herman and Chris's business was Cambridge Processor Unit. See what they did there? CPU, and they took on various techie contracting stuff, including occasionally some fruit machine maintenance. So there was a couple of fruit machines in there, which I duly learned to power up because they were crotchety, but I learned to sort of fiddle with and bang, and occasionally people would come around on a tour. And just as part of showing that the company did a variety of things, we had to power up these fruit machines. I think there were fruit machines. Certainly there was a fruit machine and a games machine, and there was comedy because the building was so full of stuff that the stand-up fruit machine was in the gents' toilets, and the sit-down fruit machine, the sort of tabletop one, was in the ladies' toilets, as is only appropriate. And also, it wasn't that well developed a building. It's the sort of place where the drains from again, the loos run down the outside of the building. And I remember leaning out of the building on a very cold morning. This is in a later job, pouring hot water from the kettle over the external pipes to try to get the drains to run properly. You might have seen Micro Men, and yeah, it's a different pub yard they used to picture the supposed 4A Market Hill. It's the one in Cambridge between the Mitre and the Baron. So as I say, that's where it is. That's the huge new Marks and Spencer's building that was built one time while I was at Market Hill. And that's another view of it. And sometimes we entered through the fire escape steps. Other times there's a door just down there somewhere. Very strange building. This used to be the electricity showroom. So I did that job answering the phones for the summer and then back to college. Christmas 1980. Naturally, I went back there because they said there's always a job for you, and they set me looking at the Atom colour board, which was a bit of a problematic thing. There was never enough red in it. It basically worked, but the red was never a strong colour. Now, just a brief diagram that I dredged up for talking about this. You know, in colour TV, this is analog colour TV, because it has to be backward compatible with analog black and white TV. The colour signal is carried on an extra little carrier that doesn't interfere with anything else. It's fast enough that a black and white TV just ignores it. And the phase of this 4.333 megahertz chrominance signal is what determines the colour. So it's on a phase diagram that runs from 0 degrees in phase with some nominal start of the scan line, which tells you where 0 degrees is. And the colours that the Atom had in its colour mode were basically blue, which is fine, green, which wasn't too bad because it's got quite a lot of the cosine, the in phase in it. Yellow, which was good because that's almost the exact antiphase of blue, and red, which is a bit too close to 90 degrees. So to express a good red, you need a good sine wave present in the thing that you're synthesizing this signal from. So the board had on it a good cosine wave from a square wave that was filtered, which is that purpley line there. And it was supposed to have a good sine wave as well. And there was a mixer between the two to give you anywhere around this color circle. The problem was the sine wave was derived just using some kind of other filter on the cosine or on the square wave. So it was this sort of nasty, gnarly shape. And I spent 2 weeks looking at this thing with oscilloscopes and dabbing extra resistors or capacitors on it, and occasionally an inductor, because we didn't really want to add an inductor because they're expensive. And well, I improved it a bit, I believe, but it was never very good. I've really put this in for any of you who've tried to use an analog TV color board with an Atom and are wondering why the color really ain't that great. So that's what I did for that Christmas 1980 job. However, following that, I did buy and build myself an Atom because by Christmas 1980, the demand for them wasn't so huge. And I wrote Atom Invaders in my room in college, which was a lot of fun. And I sold that to David Johnson Davis at Acorn Soft by summer 1981. And then I worked for them during the summer holidays in 1981, during which I wrote Atom Snapper, amongst a few other things. You see this picture here? That's got a good strong signal. Again, I just nicked these off of Google somewhere. But I assume this is connected up using an actual proper video level connector to a video display rather than having been anywhere near the analog color TV. I'm not sure about the colors on that, but anyway, that's Atom Snapper. That was a lot of fun writing that. And having realized that maths was quite hard if you didn't pay a lot of attention, I switched to computer science for part 2. And I did that, including some more work for Acorn in the Christmas holidays. And then in September 1982, when I was officially a grown-up, I phoned Acorn and said, well, I'm starting a job. We need to arrange when this happened. John Horton, who was technical director then, said, who on earth are you? Never heard of you. And I said, well, I've been working for Acorn in the holidays, and Herman said I could have a job. £6,000 a year. That sounded a lot. Well, it's all relative. Anyway, as people have described, notably Brian this morning, there were BBC micros everywhere with DFS and System 3, 4 and 5 file servers doing various stuff. There'd been plans afoot to have someone write a much better disk filing system, whose code name was Azad-DOS, which had been specified by Roger mainly at the time, Roger Wilson, now known as Sophie. Basically the hand-waving top-level spec of that, we wanted bigger directories, which were hierarchical, longer file names, more open files at once, wanted to support double-density floppies, and hard disks. The hard disks at the time were not very big, except physically. That thing there, well, that's a 5 1/4 inch floppy, which is about, 12 centimeters. And that's the same width as well for the hard disk, and that's maybe got 2 big platters and 4 heads in there. And yeah, the hard disks we had at first were 3 megabytes, 10 megabytes were coming and 30 megabytes were coming probably the year after. So yeah, the idea was that ADFS would address all the shortcomings that were giving developers working within Acorn problems because of those limitations, really. So in the first instance, we were writing it for us to use, and then obviously, because it would be great, we'd sell it. Excuse me a moment. So in theory, it would be all singing and all dancing. And yeah, gradually the name changed to the more sensible advanced disk filing system, clearly implying that the previous one was retarded or whatever. So some consequences on those decisions. Obviously there are compromises because we didn't want to use huge structures that you'd run out of memory for. We still decided to go for a fixed size directory with a fixed number of files in it so that you could load the whole thing into memory, and probably the previous one or have another one for workspace. To be honest, I forget the details, but yeah, we settled on a directory taking up 5 disk blocks, which could hold 47 entries, and they had a bunch of attributes that DFS didn't. Obviously, is a directory is a very important attribute, and read, write, execute, and locked. Locked being a bit that once you set it, you can't unset it, and you can't change the other ones. In contrast, DFS just had a single letter qualifier, which is like an extra bit of the file name, but it's your default. So if you say load Fred when the qualifier is A, it would actually load a.fred. If you say load Fred with no qualifier set, it would load $.fred because dollar was the default qualifier. And that's why dollar is the name for the root of the disk in ADFS, basically, for kind of compatibility for saying $.thingy. 10 characters in the file names. We thought we could be really expressive with 10 characters instead of 7. You know, the excitement, like Twitter going from 60, whatever it was, 128 characters to 256. More open files, settled on 9 at once as a reasonable number. But we didn't want to allocate 9 blocks of memory on the Beeb, or pages of memory when they're in Beeb's memory. We didn't want to allocate 9 256 byte pages of memory to caching. So we had 5 blocks or 5 pages, which we would manage dynamically. It wanted to support double density floppies and hard disks. Now, as a consequence on having hard disks there, you could have lots and lots of directories. Clearly, you can't see all the files at once on the disk. So you had to have a separate free space list to be able to manage that sort of stuff. And this obviously, if you've got the same information expressed in 2 places, there are opportunities for it to be inconsistent. So getting all that stuff right was a thing in itself. A bit more detail about that. Given you've got bigger directories taking up 5 blocks rather than just 2 blocks, like I think there were in DFS, if there was a power failure or some other horror like an actual disk fault or a transient disk fault, you might accidentally partially write the directory. Or indeed, if some other screw up leaves an entry in a directory pointing at something that isn't a directory, but with the directory bit set, you need to be sure it is a directory. Hence, this sequence number was put in the directory, and a piece of unique text that no one would ever write under any circumstances. My name, of course, that's why it says Hugo in ADFS directories. Twice, once at the start and once at the end. Because we had to know that the first block and the final block had both been written together at the same time. That is to say, they both had the same sequence number. Every time you write the directory, the sequence number increments at the start and at the end. You write them both together. If they match, you mean the directory was completely written and should be consistent. Using the 5 blocks of caching, 5 pages of caching for open files, we used a least recently used algorithm. Again, a fairly trivial bit of computer science, but people hadn't done that sort of thing on tiny computers like this before. Essentially, the implementation is that you've got some data describing the contents of each of these blocks, and you have a bit that's set in it. And every time someone accesses a block, you just move this bit onto the next one in the list. in a circular fashion. So if someone touches the third entry, you move the bit onto block 4. If someone touches the fourth entry, you move it onto block 5. And if you then carry on only touching entries 1, 2, 3, and 4, it'll stay on block 5. So statistically, block 5 is the least recently used one. And if you touch block 5, it wraps around back to block 1, etc., etc. So it's not inherently correct all the time, but it is statistically most likely to give you the best use of the cache. If you've got 2 or 3 open files, that's great. If you've just got one open file, it just uses it as a big circular buffer. If you were to say open 6 random access files and then get a byte from each of them in turn, you know, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, the buffer would very definitely thrash because you'd always be chasing that bit round and round. But there are always corner cases where caching algorithms go wrong. The thing would still work correctly, just really, really slowly. Another good thing that was a massive advantage over DFS of having the open file cache be used dynamically is that when you've got a dirty block that you've written, modified, whatever, that needs pushing back out to the disk, you can do that in background because you can find another block in the cache for dealing with the next one from that very same file. So you could do background commit of dirty data, which meant that, you know, you could write a file much more quickly, you could read files at the same time as writing much more quickly. It's all good stuff. As I said about hard disks, the consequences of the sizes of these things, you could have lots and lots of directories with lots and lots of directory entries, so you had to have a separate free space list. We chose to keep files a single extent, basically because the thinking at the time was, wow, 10 megabytes, who on earth could possibly make that much data in 30 megabytes? Wow, it'd be like being like in a warehouse with your suitcase in one corner, you know? So we figured that you could always move the file to a bigger area if you needed to move it. So if you open a file and you start writing it, it's distinct from just a star save where you know the size of it from the get-go. You can just find that space and write it. We kept files to a single extent, so you must occasionally move an open file when it grows beyond the pre-allocated lump you've given it. I mean, I think we gave it something outrageous, possibly depending on the size of the disk, but it was something like 16 kilobytes, which was quite a lot of data for the initial allocation. And I think that was probably picked so that you could have sensible behavior on a little floppy as well as on a hard disk. As for what to do when you extend it, the rule of thumb we used, which again just came from computer science folklore, if you like, if it got to a particular size, S whatever, chances are it'll get to twice that eventually. So anytime you extend a file, you double the amount of disk space you've pre-allocated. So the free list was 83 entries. That's because that's as many as you can fit in, really. We made them be 3 bytes of start and 3 bytes of length. That would deal with, because these are block addresses and lengths in blocks, that is 256 bytes. That's a whole 4 gigabytes of disk space. Again, we thought, blimey, that'll last a decade or so before disks outstrip the size of that, you know? Well, of course, but these days 4 gigabytes on your computer of actual RAM is a tiny amount. So yes, how things have grown, but it has been 40 years. So clearly the free list needs a lot of interesting stuff doing to it. When you free up an entry, when you delete a file and free up a chunk of space, you might need to merge it with the entry beforehand if there was free space beforehand. You might also need to merge it with the entry afterwards. So it may be that when you free up a file by deleting a file, or indeed by closing a file and then truncating it, right? Because of the pre-allocation, you might lengthen the free list by 1. You might make no change to its length by merging, or indeed you might decrease its length by 1 because of merging two entries either side. We experimented with allocation algorithms. Again, this was kind of research that we hadn't really done before. What these acronyms stand for is perfect fit, else, first fit. We did experiment with just picking, you know, the naive one is the first fit. Look up through the free space list. As soon as you find a block of free space that's big enough, just use it. And that generally gives rise to a smaller block of free space because it's unlikely to be a perfect fit. We also looked at worst fit, that is to say, use the biggest lump of disk space. And, you know, we wrote simulations for this sort of stuff in BASIC to judge what they'd do with doing random allocates and frees to see what might happen. With worst fit, you get some quite weird behavior because it always takes from the big chunk of space at the end of the disk, if you like, that's, you know, the rest of the disk. Eventually your files creep higher and higher up the disk because they always take off the big bit at the end until they get halfway through, when there's a big bit to the left and a big bit to the right, and then it alternates. So the files jump around around the halfway point through the disk because there's a huge space on the right and a huge space on the left. So anyway, yeah, we settled on if there's a perfect fit, you use it, because that's obviously good. It shortens the free space list, and shortening the free space list is actually your overarching goal, because the shorter the free space list, that is to say, the fewer entries in the fixed size free space list are used, the more choice you have when freeing up other files, stuff like that. Because of the, you know, the horror problem is when you've got a full free list, that could mean it's impossible to delete a file if it doesn't abut any other free space. If you need to make another free space list entry, it might be impossible to delete a file. Now, we could have allowed such a delete to go ahead, and that would have then leaked store. There'd be an entry there that isn't, sorry, there'd be some free space that isn't in the free list. So to be able to get over that, basically we had to make star compact, which moves files around to effectively what these days we call defragment. All of the systems we use these days have defragmentation of the disk. You know, Microsoft stuff is full of defrag your disk and also defrag the registry. There were more bugs there in getting compact to work properly than I remember, so lots of awkward stuff. As a consequence, as part of writing this stuff and trying to make sure it was bug-free, I wrote lots of consistency tools in BASIC, and that's really what led to those various disk read-write stuff. There was a hex editor for editing disk blocks and writing them back, which I kind of wrote for my use, so that if I thought, oh well, maybe that's the cause of the bug, let's just check. I'll change it back in the, you know, on the disk bit by bit, then write it back and see if things work again. So a lot of tools that were actually shipped with ADFS for allowing the user to sort things out if things had gone wrong, or at least helping them to understand what was going on maybe. Those were shipped because I wrote them as part of tools for me to sort out, to try to work out what was going on and understand what was happening on the disk. So that's really the main part of the ADFS design process. I'm not going to say a lot more about that. There was some interesting computer sciencey stuff in there. Quite a lot of it was trying to get the code short enough while being comprehensible enough that we thought it would work properly. Some internal releases were really, really low on space. So instead of having error messages that said things like can't execute, or now let's just think what the two error messages were. There was some that said I can't execute that, and one of them was it's impossible to execute that, in the sense that the addresses for loading a program were where there was no memory on the beep. And on one version, those were just abbreviated to can't and won't. But then again, as I say, these were only internal releases, and we got the space eventually. Meanwhile, partway through writing ADFS, I was redirected to look at DFS 0.9. There were lots of DFS clones around. And one slightly interesting thing I was involved in was going through a disassembly of a Watford ROM and basically proving, to the extent that was worthwhile almost having a court case, that they disassembled ours, put some labels on it, reordered it, reassembled it, and they were shipping that as their own and saying, but it's completely different. No, it had the same bugs, it had the same idioms, it had the same store layout. So anyway, I was fixing lots of bugs in DFS 0.9, which was all right. The worst bug of all was the legendary, in DFS early versions, disk fault 18. This was a very nasty bug because it happened very rarely, but when it happened, that particular floppy was unusable for all eternity. You had to reformat it. Disk fault 18 meant sector not found. In other words, we're trying to read a sector off of the floppy. It just ain't there. Writing the disk shouldn't be able to do that. It doesn't write over the headers. It only happened one time in, you know, hours of a little test program chuntering away. That's not a huge number of cycles because floppy disks don't work very quickly. Fortunately, someone in production engineering realized that it was only one make or maybe two makes of floppy drive that did this. So then at least we could narrow it down and, you know, run our test programs against only that brand. And we also slowly worked out by looking at various things that it was always the physical sector number 2 on the track. So to understand what's going on here, this is where I'm going to go off into some technical detail, but that's the interesting stuff. I'm going to have to talk about formatting. Floppy disks have got 10 sectors on a track, and there's an index hole punched somewhere in the middle there that that is looked at with a little light and a light sensor in the disk drive so that it kind of knows where to start searching. I've marked in red the block that is always being destroyed. If you've got plain formatting, the logical sectors are always just written in the obvious order, you know, and it wraps around. This is one track going round and round. You could have a thing called interleave. So if it takes you a little time to get ready for reading the next block after you've read block 1, you might use an interleave 3 so that block 2 is here. So you've got the time while these two pass by the head to prepare yourself to read in block 2, sector 2, and ditto sector 3, sector 4, and then it's another skip of 3 to sector 5, back here again, and so on. The interleave has to be co-prime with the number of tracks for it to work sensibly, because if you just go, you know, 1, 2, 3, 4, 5, then you have an uneven skip at the end. You could also have interleave between tracks, where this track starts with 1, you know, logical sector 1 in physical sector 1, but you might move it on 1 on the next track. So it was all quite hard to work out what block it was that was actually missing when you look at the track formatting. I don't really remember how we formatted the disks, to be honest, but the thing is, it was one of those things that you could vary, and various people did vary them. So anyway, formatting. It was a pain to work out that it was physical sector 2 every time, but it was. So what happens when you actually read or write a floppy disk? Well, formatting places this format here on the disk. Obviously, when you format a disk from scratch, there isn't any data in particular, but there's still data there just as an empty block. There's no concept of a block with no data. It's just that one the file system hasn't used yet. So there's a header, and then there's data, and then there's a gap with nothing in particular in it, probably written in with some pattern like A5, A5, A5 to get the clock synchronized on the approach for the next header, and so on and so forth. And bear in mind, this is now physical block numbering, not logical. So when you're reading, we read this header and go, is it block number 2? No, just skip over here, resynchronize. Is it number 2? Yes, read and send the data to the CPU, and then there's a gap. And that's what the 8271 disk controller does. It does this reading of the headers, it does asking whether it's the sector we want, and then if it is, it makes interrupts and the data is transferred across to the CPU using NMI. When you're writing, similar sort of idea. It does a read, is it number 1? And in this case, we're looking at writing sector 1. In this tiny gap here, we change from read to write, and it makes interrupts, and the CPU delivers, I think it was 2 bytes per NMI, and it can write the data. And then when we've written all the data and an error correction code and a few completions and things like that at the end, then there's a little gap during which it can switch back to reading. It reads to see, is it sector 2, because we've automatically incremented to do number 2, get the data and write, and so on and so forth. And the 8271, as I say, is doing this reading and swapping from reading to writing on the fly. And the 6502 would only get interrupts like every 2 bytes during this period and every 2 bytes during this period. That's how we do a floppy write. So how could we possibly get a sector disappear off the disk? Well, why is that gap there? The rotation speed isn't the same as when we formatted it or when we wrote it last time. The clock speed of everything might not be exactly the same. Temperature variations, you've taken this floppy out and you're writing it in a different computer entirely. It's not the same chip. It's not the same drive. So this gap is to accommodate differences in the speed of the media and the clock and everything. So it may be that if the disk is going a bit faster, more of the disk whizzes by the head during the write, so the write might eat into a little bit of this gap. Or it may be if the thing is going slower, it'll write a bit shorter than the original formatting, so the gap gets a bit bigger. It doesn't matter. In normal circumstances, that gap more than covers it enough. But what if the disk is really whizzing past under the head, but we write the data at the standard rate? The write might go far enough to destroy the header of block 2. And that's what was happening, we inferred. That was the only possible explanation for it. So we had to dive in and look at how these disk drives actually worked. What normally happens, we actually looked at them and there weren't that many wires to the motor. Normally you get the motor turns on, there's a speed wire, a speed line signal that measures the speed that it's rotating at. Ready comes up here, and then the 8271 starts reading as soon as ready comes up, and then we get to write, and that's where the interrupts to the CPU happen. With a scope on these things, we were able to capture things like this. The thing is, when this particular brand of disk drive powered up and started spinning, it overshot the target rotation speed. Every time it overshot the target rotation speed, but very occasionally it did it at such a place that when ready came up, ready comes up when it reaches the speed, ready should have actually waited until over here when it was settled on the target speed, not coming up here. But anyway, ready comes up early because at this point it's going too fast. So then, depending on timing, in this section, the 8271 would find the very first block on the track, and then we'd do the write while the disk was spinning too fast. So it did exactly this circumstance. The first block was written too long, it destroyed the header of block 2, and that was it. And the fix was boring, of course. You just add a delay. Almost every fix for hardware is add a delay to let it finish because it doesn't match the spec. Well, that's hardware for you. So that was an interesting thing, which took a few weeks of stress and peering at scopes. So I was back to working on ADFS and doing that sort of thing. Now, another interesting bug, the twos bug. By then we had tubes with coprocessors, second processors, and various important pieces of software running on 6502 second processors. I think this may have been associated with file servers that were doing a lot of asynchronous traffic, or it may just have been some testing of tube software. The tube magic chip that connected second processors to the Beeb, it wasn't that magic. It was, as I say, just a few FIFOs and whose lengths were chosen to be a good match for the sort of traffic we needed to do. I think the biggest one was from the second processor to the Beeb for printing stuff quickly, depending on what the latency and time delay of that was. Others were for sending bulk, and of course the big ones were for sending bulk data to and fro, like when you go load and save. And the others were obviously for metadata, for saying there is something in the other register for you to look at and it's of this type. So they were a standard post box, as they are sometimes called, or mailbox with full and empty and available registers. All hardware memory mapped stuff and all completely asynchronous. Very occasionally the Beeb on this would go mad, or at least the system would go mad, just printing 222222222 without any new lines to the screen as fast as it could. It was prompted by actual having tube traffic going on, like you'd do if you're running an ADFS test suite, saving and loading and reading and writing data from the tube side, or as I say, it may have been a file server, I don't know. This was considered sufficiently horrible that we were allowed to have logic analyzers. At the time, logic analyzers were big and scary. I hadn't seen one before. That's the aside about a logic analyzer. Literally dozens of wires connected to your system that you're investigating. It had all the address lines, the data lines, and read and write and clock and instruction fetch wires that the 6502 had. So it could capture all of the 6502's interaction with everything outside of the 6502, and it understood 6502 opcodes. So effectively, it would give you a disassembly listing of what the thing actually executed, rather than a disassembly listing like from the source code during assembly, a timeline of what it actually did And when it did a read, it captured what the red value was. If it did a write, you see what the write value is. They were expensive. They were 25 grand, the same as a house in 1983. Fair enough. It was a small house that I bought for 25 grand with someone else in 1983. But that was gobsmackingly expensive, and we were quite disconcerted when we realised how expensive they were, having poured a cup of coffee over one of them and gone and had someone else go, good grief, that's all right, you know what they cost. So anyway, scary things, but very powerful and useful. So the twos bug, it would fire every few hours. Logic analyzers, their power was in their programmability. You could, using their funny little keyboard on there in the display, you could say things like, wait until the 6502 reads this value from this location and then go to the next step. Wait until it reads this value from this location and go to the next step. Wait until it fetches an instruction from here, which really means takes a branch to here. So you could basically work backwards for where it was stuck in a loop saying 2222222. You could look at how it approached that. In other words, determine, having looked at where it was in that loop, you could say when the first time it enters the loop where it's stuck saying 22222, stop the capture of data, and then you could see what it was doing for probably 100 instructions beforehand. A little narrow window like that. It was basically a window into its immediate past. So you could work backwards to where it went wrong. And we found that where it went wrong was in the Beeb's idle code when it's attached to a tube, which is polling for the tube wanting to do something. Because any other activity was driven by an interrupt. If you press keys, it makes interrupts and things like that. So it was just sitting polling for the tube to tell it what to do. And I've changed the exact addresses and so on in this, and probably the exact instructions, but it was definitely a bit instruction and a conditional branch back to the very same bit instruction. So the bit instruction took 3 cycles to fetch the instruction, 1 to fetch the data, and then the branch took 2 instructions to fetch the branch and another one to decide what to do, and if it took the branch backwards, another one. So that took something like 8 1 megahertz cycles. So the point was to poll as quickly as you can so that the Beeb responds to the tube wanting to do something as quickly as you can. So that's a very, very tight loop. As I say, I already covered that. And I managed to catch it on the logic analyzer performing the branch instruction incorrectly. This is where the kind of timeline, it had done the bit, branch -3 back to here. It did the bit again, branch -3, and then it went and fetched code from BDBE. As I say, I made up the numbers, but it was something like that. This is neither taking the branch nor not taking the branch. It went somewhere else. It wasn't the branch target. It wasn't the next instruction. And we realized it was a weird mix-up of the next address kind of half calculated, not calculated. So we figured that in the 2 cycles of reading the branch instruction and decoding it, part of the 6502 decided it was taking the branch, and another part decided it wasn't. And then they fought or compromised or did this mad thing and went off into the boonies. And it's not surprising, you know, if the branch was neither taken nor not taken, that everything after that was chaos. So at the time, Roger and Steve Ferber had been thinking about this and talking to the guys who made the chip, and their answer wasn't very helpful. They really did say something which was more or less, yeah, we've seen that, odd, isn't it? We don't know what's going on. I'll explain what we think was happening. This was from Roger and Steve's best theory, metastability. To get this, there's a bit of physics in here, really. Registers are bistables. You store a bit by having a register set to 0 or set to 1, a flip-flop, a D type. They remember things, that's why they're called stable. And they're bistable because they can do 0 or 1. Now, the reason they're stable is because if they get perturbed by a cosmic ray hitting them, or electromagnetic interference, or thermal noise, or voltage line fluctuations, they'll still settle down to the state they were in before. In terms of energy, It's like a marble in a box with a triangular partition in the middle. The marble's here, it's down at the bottom of the gravity well. If you jiggle it about a bit in this half, it'll fall back to the bottom of the gravity well where it was before, in energy terms. If you find it here, it falls down to this corner. So it can be stable on one side, or if you put in a heck of a lot of energy to lift it to the top, it'll then fall down to the other side and it'll be stable there. The point is it takes a lot of energy to change it, right? So that's the kind of analogy in terms of a mechanical analogy. And in terms of energy, we think the energy graph is more like that. So a bistable actually looks like this. This is a very, again, a simple example I nicked off the web. Don't know if all of you will understand how transistors work, but basically, if this one is conducting, it's because there's a high voltage here, which means there's a high voltage here, which comes across here through that and makes this one conduct. The fact that this is conducting means there's a low voltage here because the voltage across this resistor will be high because it's conducting. There's a low voltage here, which means that this one is not conducting, which is why there's a high voltage here. And you can flip them over, in this example, by shorting this to ground or by shorting that to ground. It forces it into the other state. What actually happens in a D-type is you force a logical voltage into this point or into this point, depending on whether you're setting it to 1 or setting to 0. But what you're really doing is driving an analog voltage somewhere into this range. And if you put it in any of these points, it'll quickly settle down to over here. If you put it in over here, it'll settle down to over here, like dropping the marble in the box off center one side or the other. But suppose a synchronous system, which is looking at this memory mapped I/O as fast as it can, sees an asynchronous signal halfway through changing. It might sense a voltage which is halfway through. It might land right on top of that curve. It's like balancing a pencil on its point or balancing the ball on the middle of that partition. You could copy an analog signal into the middle of this. Now, normally it doesn't matter if this happens because probably in a few microseconds, thermal noise or the noise of basically power supply noise, clocks going on all over the place, will jiggle it about enough that it'll fall off one side or another. But what we think is happening is that, as I say, the branch machine in the 6502 saw this, and in copying it to obviously two different physical places, one of which does the first part of the branch machine and the other which does the second cycle of the branch machine, they saw them in different ways. Hence it went off into the boonies in its mad mixed up address. So it's like balancing this here, and you know, one part of the machine saw the ball falling that way and the other saw it falling that way in its copy of it. This is just a copy with this here added. So thinking about how to solve this, we realize that actually no two flip-flops are physically the same. They can't possibly be, because they're on different bits of silicon. There's manufacturing variation, etc. So you've actually got a whole pile of energy curves for all different flip-flops. And that means different bits in different registers. So if you move the data from one register to another and back, for example, it gets to be stored in several sets of hardware, as well as you putting a few cycles of delay in there that might give it a chance to settle. So they won't all have the same metastable point. The value will fall off to one or other extreme before we tried to branch on it. So the fix was simple. We just add a TAX, make it a load so it loads into the accumulator, bit 7, then move it to X register, bit 7, then move it back to the accumulator, which has the side effect of setting the minus flag in the status register. So that's a third separate bit, and then do the branch on that. And that was the figuring, that it would therefore have had to balance on all these different places, and it couldn't possibly. So the probability of failure is cubed, or better if you're confident that things will be different from one another. So this changed the bug rate from about every 4 hours to millions of transfers. Sorry, to millions of years, for about 10 to the 20, because 4 hours was tens of millions of tube transfers. Cubing that gets you about 10 to the 20 tube transfers, which was millions of years. And in fact, the time taken for these are single cycle instructions. It increased the latency of responding to the tube by less than a half. So we thought that was okay. So that was an interesting excursion, and that was kind of where I got to be an expert at logic analyzer programming and poking at things like this. And it stood me in good stead. You know, in later jobs I've dealt with systems debugging, Bluetooth chips and things like that, where you have logic analyzers with not dozens of wires to the chip, but hundreds, because you might have, you might have a 32-bit address bus and a 32-bit data bus, or 16 bits and a lot more stuff going on. Anyway, then after that, basically finished ADFS in the sense that anything's ever finished, and it was time to do ADFS for the Electron. Well, it had been written well, and it just worked. That's the point of these sideways calls and interfaces and vectors and so on. I think the main changes were the hardware that controlled the hard disk and the hardware that controlled the floppy disk. I think it was a different floppy disk controller, so someone had to write different drivers for that, but I honestly don't remember if it was me or someone else. But horror of horrors, Stardot COMPACT would occasionally wreck the disk. This was bad news. There was terrible time pressure to get the Electron out for Christmas in the hope of capitalizing on the huge boom of people buying computers for their homes. So we kind of assembled a tiger team with consultants. This wasn't all just on my account, incidentally. There were other bugs. You know, we didn't have a tiger team and external consultants just because of this ADFS COMPACT thing. Top Express were the company that were consulted. They'd helped Acorn with various things, and they used to have offices in Bridge Street, upstairs above what's now La Margarita. I don't remember if it was La Margarita downstairs at the time. But yeah, those offices up there were Top Express's offices, and those are the windows behind which we worked. I can remember looking out of that window, enjoying the morning traffic just starting up after an all-nighter. Enjoying is assigned value. But interesting times. And it's interesting that kind of 20 years later, I started going to La Margarita quite often with a gang of friends and sitting upstairs, and it gave me funny, weird, scary feelings, and it took me, stressy feelings, and it took me a while to work out why. The previous time I'd been in that very room had been in a time of incredible stress and hassle and hard work and sleep deprivation. Obviously, I'm totally at peace with it now, but it was kind of weird when I realised, blimey, I know why this room feels familiar yet alien and weird. It's because I pulled all-nighters here getting Electron ADFS to work. Anyway, so we did all this. We spent lots of time poring over the code, looking at stuff. You know, how could it go wrong on the Electron but never go wrong on the Beeb? Nothing's different, but it did. And then at about 4 in the morning, it was just getting light. John Thackeray, after he'd been reading through stuff with me, and we'd probably read through the Stardot COMPACT, and probably his subconscious would go, there was something else you ought to do. And he finally said, the cursor, the on-screen cursor on the Electron is software. Well, it was a timer interrupt. The cursor on the Electron modifies the screen memory. On the Beeb, it's all hardware. No screen memory modification occurs. So you can happily do Stardot COMPACT using the screen memory as your buffer for moving files around in huge chunks, without the screen memory getting corrupted, even though the cursor is flashing away. It's separate hardware in the video feed doing that. But yeah, that's exactly why it was being corrupted. So basically, we did the VDU23 whatever command it was, reran the tests rather anxiously. It was fine. I even put together a version of ADFS that had the turning off the cursor built in. But as it happened, the candidate ROM had a bunch of other problems solved. We'd got it all working rather well. The real point is that we were confident that we knew what the issues were, and that ROM had been thoroughly tested. So it was a good candidate, as we'd say, and the fix for this issue was simple. And there was time pressure to get the Electron out for Christmas. So the ROM without the fix was shipped, and we sent a basic program that just turned the VDU off for you and did COMPACT and then put the VDU status back afterwards. Unfortunately, the Electron was late for Christmas anyway, and that was kind of the start of Acorn's doom, because by then the personal computer market for hobbyists and students was getting saturated, and that was the start of Acorn's financial problems. Really made hundreds of thousands or maybe tens of thousands of Electrons, and essentially they had to be pulped or sadly landfilled. because of all that plastic and poison and stuff. So that's why the Electron was shipped with that bug in Star Compact. We'd found it, we knew how to fix it, but it was a management decision in the sense of managing the risk of making a late change to the ROM, that it was decided to ship it without that fix, which some of you may have been interested in. So next, as Brian alluded to this morning, I was signed up to Project A, top secret. It was the ARM CPU. It's the only thing I've ever done that was actually pointful in the long term. We did sign this internally and NDA kind of letter, no talking to everybody else unless they'd been indoctrinated. It was thrilling stuff. It was a lot of fun. Again, as Brian said, the museum's got one of those letters with all our names on it. And as an aside, Project B was the Master 128 with the sideways RAM and all that, which had a similar veil of secrecy, you know, for good reasons. There were always journalists who'd come to you at shows on those rare occasions we worked shows who said, oh, is Acorn working on a new version of blah, 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 blah? Are you looking at improving this, that, and the other? And I was always tempted to answer facetiously, no, we've got an enormous pile of money and we just sit on it giggling all day. Because of course the company's working on improved things, but saying the company's working on improved things, they'd just make up a story, wouldn't they? Anyway. So, of course, we were working on improved beebs. We were working on the ARM. I'm sure everyone knows why Acorn was working on the ARM. It wanted to go to 16-bit or 32-bit machines. And basically all the candidate 16 or 32-bit machines you could buy were far too expensive or too expensive to use in a system because they didn't have the interrupt latency. They didn't respond to interrupts fast enough. And part of the point of the 6502 and the way Acorn had done things in the Beeb was quite a lot of functionality that would normally be done by a DMA controller was done using NMIs. Floppy disk data transfer and Econet data transfer, those were all done using NMIs. And we wanted to do the same with ARM and make it fast enough. So the question is, how do you make a completely new CPU from scratch, from nothing? Well, emulators. You have emulators, lots and lots of emulators. And tests. We had a test suite. I wrote a test suite more or less, and a bunch of other code fragments to prove that we could write FIQ routines, to do this, that, and the other, to prove we could do fast copies, to prove we could do various other little programming idioms, for example. Two of the instructions, reverse subtract, which is only pointful if you've got a constant, so you can do 10 minus x in one instruction rather than having to do x minus 10 and then swap it somehow. And the compare negated as well, so you could compare quickly with negative values rather than having to do an ordinary compare and somehow fudge how you use the flags. Those are kind of my ideas that came out of writing those things. So we had a lot of simulators of different types and test stuff, not least to verify that the documentation was unambiguous, the design doc was unambiguous, because if the simulators agreed with one another and the test suite, then you knew they were all going to be the same. And of course, a chip design team to make the silicon, but that was all kind of funny people downstairs with big expensive computers. So one emulator was in BASIC from Roger and Steve, and that was the first one that defined what was supposed to happen. There was a basic one, I think, done by Steve and the chip design people that was more block by block, kind of a halfway model to the chip architecture, but where registers with numbers in were represented by variables with numbers in, as opposed to an array of 32 flip-flops. John Thackeray wrote a very fast one in 6502 that we mostly ran on a tube for testing, and the hardware simulator on the Apollos that was really, really slow because it was actually simulating the chip gate by gate, flip-flop by flip-flop. So how do you test something where you know nothing about what already works? I really had to build from nothing whatsoever. This sort of thing. Load a 0, check that the chip thought it was a 0. Load a 1, check that the chip didn't think it was 0, etc., etc. And because we didn't have any loops or anything yet, you know, what I mean is at this stage in the test, you haven't verified that a branch instruction will even take a branch. And you don't know that arithmetic works, so you can't count through a table. So the whole piles of just do an add of 2 numbers and check you get the right answer. and they printed things that just used SWI0 because that was built into these simulators as a printf, like Brook on the 6502. And I think SWI non-zero was emulated, and that's how we tested that, but I can't really remember. So thus you can bootstrap your understanding of what works. And then eventually you can do complicated stuff. And the final complexity was running each of the other cases with interrupts happening all over the time, over all of the time of the test. So if you've got a test that took 100 cycles, you run that in a loop with an interrupt happening at cycle 1, the next time at cycle 2, and. So that was n cubed time for each test. So those took a long time to run, even on the good simulators, on the fast simulators. But this proved at least that every instruction was uninterruptible and restartable. Now, of course, that doesn't necessarily apply in the simulators, because there's nothing hard about doing an interrupt, but having the silicon do it correctly is another question. So having those for testing the actual chips with was really useful. I think we actually managed to make a timer that did that somehow. So lots of tests. The fast simulator would run it in a couple of minutes. You could run the lot in 10 minutes. The interrupt tests in half an hour. Block simulator would take hours. The actual chip layout sim took days and days and days. And I really don't think we ran the full suite on it before tape out. But I think, yeah, we definitely ran the full set of simple tests on the layout, and maybe ran the others while it was waiting for the silicon to come back from the fab. So I wrote lots of tests, as a consequence of which we had good confidence in the CPU matching what it was supposed to do, and the simulators and the documentation matching. So ARMS came back and they worked. Well, there was one minor bug, but that was easy to fix, and they fixed that for Silicon version 2 anyway, very easy. And we ran the test suites on the chip, and it was all very good. Marvelous stuff. And it was a bit of a corner case. Rotate right extended, which I think was specified by saying rotate right, but with an immediate rotation of 0. In other words, do nothing. And that was decoded specially to do an extended rotate of 1 bit through the carry as well. So that was good. At this point, we're an hour into it. Amazing. We'll have questions at the end, direct them in chat to the moderator, and we'll see how long we have left after I go through the last bit of stuff. Okay. After that, I worked on a variety of projects, ARCs with Acorn Research Centre, as Brian mentioned again. That was a lot of fun, but they didn't really get the idea of making a product. They also didn't get the idea of actually writing code for performance. I mean, we had conversations where, oh, but you can infer this by enumerating the database, and you can infer that by querying the server. Yeah, but you don't want to do that. You want to cache it instead. So that was taking ages and not going anywhere and not being useful. So another team, quickly put together by PMF, among other people, did Arthur, then Riskos. And it was kind of ironic and frustrating, because before we started working on ARCs, John Thackeray, Jez Wills, Brian and I and a few others had basically said, let us have at it, and we'll make a BBC micro-like operating environment for ARM development boards, for ARM boards, ARM computers. We could have had that going probably in 6 months and debugging in 18 months, but we didn't have a plan for a GUI, to be fair. And all the project planners said, oh, but it'll take at least 18 months to get the hardware ready anyway, because the chips were not really in production and so on and so forth. But yeah, we kind of felt a bit vindicated in that, you know, ARCs ended up, despite our best efforts, not really cutting it, and Arthur being put together along the lines of what we'd been saying we should do a year or maybe 2 before that. ARCs was a waste of time. It was just too ambitious. Then I worked on the floating point coprocessor, which we rather crudely named the floating poo, because that's the best pronunciation for FPU, isn't it? That involved ARM coprocessor instructions. By then, ARMS had that the external coprocessor hardware bus, where some instructions effectively caused external signals to waggle. And if some external hardware waggled a line in response, then the ARM would just kind of shut its mouth until another cycle was until another wire was pulled and data came back. During that time, Olivetti was starting to look at Acorn's stuff. Olivetti had taken a shareholding in Acorn, and I visited them with a floating point accelerator card to fit to one of their RISC-X machines that Acorn had been doing. And when I came back, I had to leave it with them for a while. And then later, Olivetti sent the card back to me. And in them days, when Britain wasn't quite part of the EU, let's not go off on one about that, things required customs declarations. And being Olivetti, everything they shipped anywhere was labelled typewriter parts. This came back to Acorn's goods inwards, addressed to me as typewriter parts, and essentially I was called up before the admin people to be told off for ordering typewriter parts when I was an engineer. I didn't even have a typewriter. We talked at cross purposes for a while, and I sort of said, what is it anyway? Olivetti, they've used typewriter parts as a generic label because one assumes Italian customs just knew Olivetti ships typewriter parts. That's what they do. Then I actually shifted across to work on RISC-X itself, looking at BSD and Unix. And during that, I implemented TCP/IP over Econet, or rather IP over Econet, which involved basically taking the Econet station number and putting that in the MAC address with a load of zeros, and essentially just sending out the packets, and then it worked. And then I left Acorn to do other stuff, all of which ultimately turned out pointless compared to working on ARM. So you might think that was that. But actually, I got a further last laugh, sadly at ARM's expense to an extent. 5 years or more after I'd left Acorn and after ARM had spun out, they were busy doing the things they do. They were still using my test suite in-house because it was fine. I very much doubt they changed the binaries. They probably lost the tech to rebuild them. It's not even clear whether they still had the source to them, but they were using these binaries that you can run on ARM chips, and they were known good binaries. But they had one customer with whom they did a significantly different deal, and that was Digital Equipment Corporation of the legendary VAX PDPs et al. Anybody remember this logo? Those are the days, eh? I should stress, again, I didn't work for them. I was working somewhere else. So DEC licensed the ARM architecture from ARM. Not a design for a chip. They licensed the architecture so they could make their own clones and still pay a license fee, probably a smaller license fee, I don't know. But it's a reasonable thing to do because ARM wanted to grow the ecosystem. And people who make stuff are always happy if they can second source things. So if someone else made ARMs, that would make the market in general happy. So DEC implemented their own ARM compatible CPUs that they called Strong ARM. Later they were called X-Scale. When that part of DEC was bought by Intel, it changed to X-Scale, and I think those chips are still available from Intel. They use their own expertise in fast chips and fast memory access hardware and caches and stuff. Good for them. But how do they test them? ARM released the test suite in binary form. I don't think ARM had generally done this with customers who made their own chips but licensing ARM designs, but I'm not sure. But in any case, even if ARM had released the test suite in general, mostly, well, it hadn't ever been a problem for anyone before because the chips that other people made that had been designed by ARM worked correctly. So the test suites never threw up any error messages, right? It was fine doing it that way. But the problem was Digital wanted to use the test suite to check that their chips were working correctly. The problem is they weren't. And as it happened, it was the shifter again. There were two problems here, which was almost a sort of international diplomatic incident. When I wrote the ARM test suite, it was for my mates. There were 10 of us. We were all good mates. We went out drinking together. It was very informal. So, of course, the messages were very informal too, a little bit sweary in some cases. DEC were very straight-laced and serious, and they were not at all happy with the slightly sweary message that they got when it turned out the shifter on their chip didn't work. The test was right. Their shifter was not working correctly, but the test informed them of this in a slightly emphatic way, shall we say. In due course, the guy who'd been dealing with DEC was Dave Jagger, I think, sent a very telling people off sort of email all around ARM, saying how terrible this was. How could we release such unprofessional software? This is so bad. Who cleared this for release to customers with sweary error messages in it? And some of the other people who'd been at ARM from the start laughed a lot, told him it was me that wrote it. And you know, he sort of went, well, who the hell is this? We must find this person and stop them. And pointed out that I'd never even worked for ARM, and it hadn't mattered all the sweariness in the error messages because everyone else's chips all worked correctly. So that was very funny, and is occasionally alluded to in other people's presentations. I think Steve Ferber referred to it as Hugo's legendary profanities when he did one of his Story of ARM talks that some of you may have seen. So that's about it from me. I think that's been an hour and 10 minutes. That's not a bad fit for the time. Any questions? And what should I do now? Unshare my screen or what?
Yes, please.
Very well. That's the final and stop share. And I'm back in the room.
Okay. So we've had a few questions come in and a couple of comments. So Brian Coburn, I think you said you wanted to comment on the DFS name qualifiers. Brian?
Is Brian still there?
I am still here. Thank you very much, Hugo. It's not past my bedtime yet. You alluded to the fact that the qualifier was $. I believe the early DFS for systems, the default qualifier was space.
Oh, you.
And that was one of, and that was one of the changes for the formatting of the disk, was that it required different qualifiers to be written onto the unformatted disk, the post-format disk. And there was a point where systems and atoms used space, and then for the beads we moved to $. So there's just another historical nugget for the audience.
Yeah, I don't know. I really can't remember. I suspect that the problem with it being space might have been that then .fred was the same as space.fred, which you couldn't really express in a string very easily. It is also the same as Fred. But anyway, yeah, indeed. It was a silly system, that qualifier thing. But yeah, I think the idea originally was just to let people have, here's my set of files, and now we'll change to the qualifier to 2 and build the new version. So it might have been a way of doing source control for tiny projects as well. But yeah.
So I think it was more intended for multiple people sharing a floppy. So you'd use qualifier H, I'd use qualifier B,
yep,
etc.
Yes, it could well be. I'll also do a brief aside about stuff that we put in ADFS. We had quite a lot of fun thinking up trick things to do with other comedy characters that we weren't going to allow in file names because they'd cause confusion. So that's why we had the hat for the parent directory. Rather than actually using up a directory entry to describe the parent, we had an up arrow for the parent directory. And I think we used backslash for the previous directory that you'd been in, because that was a very easy thing to implement. In that, you know, you had $ meant go to the directory that's the root of the disk. So that's disk block address 2. Always $ just meant the directory at address 2. Hat meant the parent directory that you always wrote down in the directory itself, so you could get that because you had the current directory in hand. Backslash was the previous directory, which just involved storing a 3-byte directory address somewhere, easy as that. And there were a few other comedy characters that you could put in at the start of a path for doing stuff like that. So yeah, we tried to just put in shorthands that were as convenient as possible. Oh, and also @ was a shorthand for the current working directory, which you might think is pointless, but consider that you're programmatically making up names of files that you're about to manipulate. Rather than having to say, is this blank? If so, just use the name Fred. And if it's not blank, put thing.fred. You could just set the prefix to @ and always write @.fred, and it will just work. So that's the reason for having a character which is a shorthand for the current directory, because you know, as I say, you would think naively you no need for this because things are always in the current directory anyway by default. But it's for specifying it where it's more convenient to always specify something. You can have a non-blank way of specifying no change. So
Okay.
yeah, just an aside there.
I'm going to now chip in with a couple of questions. I think we've just about got time for 2 or 3 maybe.
Sure.
So John asks, was there any filing systems you took inspiration from when creating ADFS or ADFS, as you call it? I've not heard it ever pronounced that way before, but anyway.
Really? Well,
No.
I'll answer these questions in reverse order. If you say ADFS hundreds of times a day, you end up pronouncing it ADFS. And the thing is, in the very early days, we'd been pronouncing it as a DOS. So just having something that started at ADFS was quite natural. NFS never quite got that shortening because it's not pronounceable in the same way. It was never, but yeah, ADFS, well, adds a word in itself anyway, it just worked. Inspirations, well, at that time, the only file systems I'd really used and been aware of was the Acorn file systems in System 3 file server that I'd used speaking to via an atom in holiday jobs, which was the similar sort of thing of hierarchical directory and dot for the separator. And I'd also used the university mainframe, and that basically you had a flat directory. In other words, every person had a directory, and in that you could put a number of files. Those files could be partitioned data sets, as they called it, because a file was always a single disk block. No, a file was always one or more tracks. A track was 13 kilobytes, and that was considered to be a massive waste of space if you only wanted a tiny little program. So you used partitioned data sets, and they were all a pain in the arse. So really the inspiration was just, let's have it, for example, yes, it must be case sensitive. That was a thing to take away from the university system. And yeah, files need to have attributes such as executable or not. And that in particular, they needed to store their load address and their execute address. Those need to be different, so you can load a thing in memory, but the place you jump to isn't the exact same place, right? And you didn't want to even limit it by having a load address into memory and then an offset into which you'd jump, because quite often we wrote nifty little programs which loaded perhaps a little bit of data and then did a jump into some OS call actually directly, or into some part of the ROM in case of some very naughty programs where we knew what was going on and it was running on the Beeb side and definitely never on a second processor. So, it was all kept very general, but most of the inspiration, well, it wasn't me, right? Roger and Steve had specified this stuff by looking at the file server and their experience of various other more mainframey systems. So yeah, I mean, we just threw lots of good ideas. And then it was really, what do we want from this to be able to write the software that we want to write? I mean, to clarify, once I had an ADFS that actually worked enough to be usable to load and save, even if not read and write open files, if you like, those were distributed to people with as much hardware as we could. So people writing basic programs or doing other things, maybe the assembler worked with it, being able to load on, being able to do a load rather than open and read. I don't know. The point is, I was on a weekly or, sometimes several times a week, pushing fresh ADFS ROMs to everybody else in the department, maybe 10 or 15 people, with this should be the same as before, please test it, tell me if you find any problems, or requests for improvements or whatever. So it was very much an informal thing. I mean, that spec of AZDOS, as I say, came from Roger and Steve. And then we just built on that with trying to get stuff going to suit ourselves, really.
Okay, thank you for that answer. And we've got well, I'm going to ask this next one. Question from Ed, which is about something called, or we believe to be called, the extended second processor, which is 6502 with 256K of RAM. Do you have any recollection of it? Oh, he's cheeky. He's got 3 questions. Any recollection of it? How was it designed, and what was it used for?
Well, if you'd asked me out of the blue this morning, I would have said, I vaguely remember the name, and that's all. Having seen Brian's answer to that, I remember a bit more. That's jogged my memory of thinking, yeah, that makes sense. Was it Brian's answer, or, oh yeah, there was also some talk about that in another context briefly. Yeah, I vaguely remember it existing, but I honestly don't remember what it was used for. It might well have been used as the special thing for assembling the Beeb OS without having to break it into bits and do a 2-pass assembly of lots of separate bits. But I really don't remember. I suspect it'll be John Thackeray you need to ask that of if you're going to get a proper answer.
John made heavy use of it, and he's going to talk about it later on. But the basic design of it was Steve Ferber came up with a way of adding more memory to the 6502 second processor. What he had was an extra little bit of hardware that followed the data bus and the I bit coming out of the 6502 that said whether it was fetching an instruction or not. And it looked for the opcodes that corresponded to all the indirect Y addressing modes. And if you executed an indirect Y addressing mode, like a load or a store or whatever, then it would sneakily flip a latch that paged in one of 4 64K pages of RAM for you based on 2 bits out of the corresponding page 3, as in 0300 memory. So you could set up what you wanted that mapping to be in page 3. And there were things like, it's called the 6502 Turbo Tube processor at this thing, and there was Turbo Masm, the assembler, that could assemble much larger programs, including, as Hugo said, the operating system.
That rings a bell now you've said it, but if you'd asked me about it this morning, I would have gone, no idea.
Yeah, and obviously you can only put data in the upper parts, you can't put code. So it was just about having a giant symbol table, which is what was needed for big things like the OS.
I think I've got a copy of Turbo Basic somewhere, which used it, and also a 6502 Turbo Tube emulator. If anyone's interested, amongst my collection of bits and pieces here.
Yeah, confusingly enough, I have a recollection that all kinds of people made products with turbo glued on the front of the name, though. Right, there were all lots of people who were making, DFS compatible things, or their own disk filing systems would be called Turbo DOS, and I don't know, other people selling hacked ROMs claiming to support Turbo Basic, where they'd made some improvements. People would just put Turbo on the front of things. So, Googling it may not help you, is what I'm getting at.
Thank you so much, Hugo, for giving us a great presentation and some very cool and detailed insights into the file systems. That I'm sure it was a pretty eye-opening for a lot of us that have been aware of 1 or 2 of those bugs in the past and how they existed and how you solved them. So Thank you very much for that, Hugo.